go back and recompute it, like for, all the back data. You have to cope with the descriptors you have and find maybe a better way to compress them, but you cannot necessarily recompute them. So also at one close to 100 million descriptors, represent. You can compute the KNN graph, the graph that links all the images. Your samples here to, to your hypercube. Okay. So who's familiar with LSH, local sensitivity hashing here? Okay. No. So for those of you who are not familiar, for instance, in the case of LSH, how do you achieve this? It's very simple. You take your data and then you project it onto random vectors, typically Gaussian vectors, and then if the output is positive, then you say bit 1, and if output is negative, it would be 0, and then you repeat it for plenty of random directions. Okay? And then one of the great advantages is that you're guaranteed that the Hamming distance, so the distance that computes the number of times your signatures agree, where they have both 1 and 0, gives you an unbiased estimator of the cosine similarity. Okay? So there have been many, many improvements. Some of them I talk about later about this. The main advantage of these techniques is that now, since you're in a binary space, the similarity of the distance between two signatures can be computed extremely efficiently with assembler operators. Especially, this just involves counting the number of times the bits are similar in two signatures. Can be done efficiently with an operator which is called, like, for instance, pop count, which counts the number of ones and zeros you have in a signature. And you have very efficient SSE4 instructions to do this. So this is extremely, extremely fast. The issue is that you put a big constraint. You want to be, like on the edges of the hypercube. Another class of technique called product quantization, which was introduced by Jigbo and colleagues at INRIA, completely forgoes the requirement to be projected on an hypercube. Okay? What this technique involves, you have like a large vector which you want to compress. What you do is first you separate it, you cut it into small subvectors. Let's say your vector is 128 dimensions. So you cut it, for instance, into 16 vectors of 8 dimensions. And for each of the 8-dimensional subvector, you do some k-means quantization. And you quantize your subvector with the quantization index of your of the closest centroid. Okay? So For instance, let's take a concrete example. I have a 128-dimensional vector. I have 16 subvectors of 8 dimensions. And then for each 8-dimensional vector, I can quantize it on 8 bits. Okay? Meaning I have 256 possible centroids. Then in the end, I will encode my vector on 128 bits. Okay? And now, let's imagine that X is my query and Y my database vector. If I want to compute, the distance between the two will be the sum of the distances over these small subvectors. And then what I do is I don't have access to the database vector itself, but I have access to its quantized estimate. So one of the nice things, there are many advantages. First, you're not limited to binary embeddings, which is much more powerful. And the second advantage is that here what you can see, the very nice property is that your query, you don't necessarily need to quantize it, okay? So this is a huge advantage because you can get higher accuracy. Typically when you query, for instance with a new object, since you query, you need to keep it only in memory for a short amount of time, you don't necessarily need to quantize it, okay? So these two classes of methods have different advantages and disadvantages. Okay. So here I could have put LSH. Here I put ITQ, which is like a much improved version of LSH. All these binarization techniques, so here comparison is context-free, meaning that the comparison, you don't need any external data to do the comparison. You just have your two binary vectors and you compare them, so you don't need any extra memory. It's extremely fast. So here, I think it was for 128-bit vectors. You can see that you can do more than 1 billion comparisons per second on a standard CPU core. I'm not talking about GPU. But here, so this is on a standard benchmark. I'll come to the results later. The precision is not so high. So here precision is measured between 0 and 1. And on a standard benchmark, these are not the methods that will give you the state of the art. Other quantization type of methods, on the other hand, have much higher accuracy. But then they have other disadvantages. They're much slower. Why? Because you cannot use anymore this very fast instruction which I mentioned before. You need here, and part of the reason is that if you're not context-free, you need to have access to your quantizer centroids, okay, to compare the distance between two images. Okay. So the obvious question is how to get the best of both worlds. Can we have the speed which we have here and the accuracy which we have here? And the answer is yes. And that's the work we will present in a couple of weeks at ICCV 2016, which is called Posthumous Code, and this is a joint work with Matthijs Tools and RVGU and both at Facebook. So the idea of Posthumous codes can be linked back to an old idea in coding. So let's assume you have a signal X, which can be a vector, which you want to send over a channel. There are two sources of distortion which are possible. Of course, first, the encoding distortion. You don't send your signal as is. You first, encode it in some way, and then you lose information. But then, when you send it over a noisy channel, some noise might be added. Okay? So in the end, you don't even, retrieve this enc, you retrieve something else. Okay? And so the question is, how do you do to optimize your encoding here so that you're not too affected by the channel noise? Okay? And the solution which was proposed in the literature is to optimize the index assignment. So take k-means, okay, just to explain. So in k-means, you cluster your samples into centroids, and then, for the quantization, you replace your sample by the closest cluster centroid, okay? And your cluster centroid, the numbers that you assign them, typically they're meaningless, okay? The assignment is just random. Assume you have like 256 centroids, which are ordered between 0 and 255. There is no reason why centroid 0 should be closer to centroid 1 than to centroid 255. If you optimize the assignment, what you want to enforce is that centroid 0, which is encoded, for instance, that's 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros, corresponds to a centroid which is close to the centroid of 0, 0, 0, 0, 0, 0, 0, 1. So this is what I show here. Here you have k-means. I think you have something like 16 centroids here. So 16 centroids are encoded over 4 bits. And here you have like a random assignment of the centroid indices to the clusters. Okay? And what we show in red is for each cluster the 3 closest centroids. The 3 centroids which are at the 4 centroids which are at Hamming distance 1, meaning the 4 centroids whose have just 1 bit of difference. For instance, 0, 0, 0, 0 is at one Hamming distance of 0, 0, 0, 1, of 1, 0, 0, 0, and then of 0, 0, 1, 0, etc. Okay? And you can see here there is no structure. Okay? While what we would like to achieve and what we achieve with the polysemous codes is that we shuffle. The structure is exactly the same. The partition of the space, the centroids are exactly the same. What we just change here is the index assignment. Okay? We shuffle, like these, index assignments, so that those centroids which are close in Hamming space are also close in the original unquantized space. Okay? And again, this is not a completely new idea. This is definitely an idea which comes from the signal processing community. Now the big question is, of course, how do we do this shuffling of assignment? I'll come to this in a second. Okay? But before I go to this, now here is the central idea, one of the central ideas of the papers. So we start with PQ codes. Again, to make it simple, just assume that you have, instead of splitting your vector into subvectors, you have just one centroid per vector. Okay? And now what we do is these PQ codes, we interpret them as binary codes. This is exactly what we showed here. Here, instead of writing code 0, code 1, code 8, we wrote them in the binary format. Okay? Code, yes. We wrote them in the binary format. And now what we propose to do is a two-stage comparison, where first we view these PQ codes as binary, and then we compute a very fast Hamming distance between the PQ codes. And then, if the PQ codes are close enough, then we go to the second stage and compute the distance in the PQ space, which is much slower to compute, as I showed you. But then we do so only on a subset of the vectors, those which have not been filtered by the binary comparison. So this is what is shown here. First, you have your query and your database item. If the Hamming distance is below the threshold, then you compute the PQ distance. So you have a simple two-stage comparison. And now, how do you find the permutation, which we call, pi, such that, what do we want it to achieve? Basically, we want to find a permutation of the indices, such as the Hamming distance between the permuted indices. So I have a sum over all pairs of indices. I have the permutation of indices I and j. I have the Hamming distance between these indices. This Hamming distance matches the distance between the centroids. Okay, the distance between the original PQ centroids. And then, of course, we have to add a couple of terms. So the optimization is over all pairs of centroids. Here we have to add a linear function to correct the scale, because here the Hamming distance, of course, if you have like 4 bits per code, the Hamming distance is between 0 and 4, while here the distance might be completely arbitrary between minus infinity and plus infinity. And then we also added a weighting term to favor nearby centroids. Our goal is not to be able to replicate the distance very accurately between centroids which are very far away, but those which are close, because these are those for which there is the most ambiguity and for which we want to be very accurate. So here, how do we optimize this objective? Now we are optimizing over a space of permutations. Okay, so it's not your standard, gradient optimization. So we got inspired by the literature in signal processing. This is a simple, simulated annealing procedure where we randomly sample two indices, try to swap their indices, and if there is like an improvement in the objective function, then we update with a certain probability. Not necessarily, but with a certain probability. And for the data we had, this is, like a very fast process. It takes a couple of seconds on your standard CPU, so it's really negligible. So again, this is what you have. So you have your two vectors, which are encoded with PQ. Okay. So you have two vectors. Here on the x-axis you have the true distance between these vectors, and here you have the Hamming distance between the PQ code if you don't do any optimization. So of course, if you don't do any optimization of the indices, the Hamming distance between the PQ codes is completely meaningless, which is why you have these points which are scattered all the way. Here you have, like the true distance versus the distance in the PQ space, and of course there is a very strong correlation. And here you have the true distance between the Hamming distance if you interpret the PQ code as binary, but once you have done your optimization procedure which we proposed. And of course the correlation is not as strong as in the case of the PQ codes. We don't pretend we are as good, but then there is much more correlation than in the case where there is obviously no optimization of the permutation. And you can see that here again, since we are much worse than the distance in the PQ space, this tells you why we still need this two-stage strategy, which involves first doing this thresholding, and then still using the true PQ distances, which are much more accurate. So all the details are in the paper, which is online, so I won't go too much into details. Here I will just show you, I will just focus on this figure, and I can talk about this one offline if some of you are interested. So what does it show? It shows here precision, and here you have the search time. So of course, what you would like to be is, like have a high precision and be on the left, of course. On the right. What you want is to be here. And what we show are 2 points, PQ, which is this approach, which is quite accurate, but which is quite costly, and ITQ, which is a binary approach, which is very fast, but on the other hand, which is not so accurate. And here we show plenty of points, the different crosses. What they represent is different filtering threshold. So remember, we have this 2-step strategy here where we first compute the Hamming distance, and if the Hamming distance is below the threshold, then we compute the costly distance. And the different points here correspond to the different threshold. And what is quite remarkable, so here for instance is a threshold of, if the distance is smaller than 30 bits, then you go to the costly computation smaller than 34 bits, 38 bits. And what you can see is that here we can find operating points where we have almost the same speed as a pure binary approach, because we managed to filter out quite a lot of points, but still we get pretty much the same accuracy as PQ. So in the paper we had like a comparison and a benchmark of 1 million vectors, where we report results which are 10 times faster than the best reported results of the literature. So part of this is because Hervé and Matthijs are extremely good coders, and just their implementation of the state of the art was something like 4 times faster than what was reported in the paper. And the method itself, this polysemous code 2-step strategy, actually accounts for 2 to 2.5, a factor 2 to 2.5 in terms of improvement, which is quite remarkable. So now that we have this very efficient tool to compute distances, we can build graphs on images. So here as a test bed we use a public data set, the Flickr 100 million data set. It's a public data set of Creative Commons images. You have the image plus the metadata, type, GPS, user ID. And in our experiments we used as descriptors the output of the fully connected layer number 7 of an AlexNet architecture, which we subsequently normalize and reduce to a PCA to 256 dimension. So what we did is use each image in turn as a query. So we performed in this database of 100 million images, 100 million queries. And on a good machine, but I think like not an incredibly good one, I think one similar to what you can have access to here. It took approximately 7 hours to compute the distances. And again, this could have been speeded up because here we just did 100 million brutally 100 million searches in the database. Okay, while there are techniques to speed this up. To be honest, we couldn't do much more than 100 million images on a machine currently, not because of the speed, but because like of the need to store the graph, and just storing the graph takes an enormous amount of time. So here the graph is for each of the 100 million images. We store the 100 nearest neighbors. So, of course, and this is not something new, you can view your graph as a Markov model, where you can go from one node to another connected node with a given probability. And then you can compute, of course, the stationary distribution of this Markov model. So this is typically the algorithm which underlies the page rank algorithm. Basically, the more a node is connected, the higher the probability that you will end up in this node at some point. Okay? And the stationary distribution can be very easily computed as simply the highest the eigenvector corresponding to the highest eigenvalue of your transition matrix, and the highest eigenvalue is 1. So it's very fast. Like the standard way to compute this is, you start from a random distribution. You assume that you can be anywhere in your graph, and then you take your random walk matrix and multiply it by your distribution, and then you normalize, and then it will slowly converge to your stationary distribution. And then the modes that you obtain, meaning the nodes which are of high probability, typically of higher probability than the neighbors, are your centroids, your local maxima. And so this shows a couple of local maxima which we have found, which show what typically you have in this Flickr 100 million database image. Of course, there are quite a few monuments, cats. This is not novel that people on the internet are very interested in cats. We have baby faces, etc. Okay. So this shows that now once your KNN graph is computed, then you can very easily do some things such as clustering. A fun thing that we tried to do also was find the shortest path in the graph from one item to another. Okay. And there are many ways to define the shortest path. You can refer to the paper to see the definition. It can be the number of hops. It can be the minimum distance among all the hops you do to go from one to the other, or the minimum of the maximum distances, etc. But here, we go from one object to a similar object, from one flower to another flower, and you can see that the transition makes, pretty much sense. That you go smoothly from one object to another. I have other examples like this, going for instance from a lion to what I think is a cheetah, where you can see that you transition pretty smoothly, from really focusing on the face to actually then zooming out until you see the full animal. Again, you start from here and you want to go here. What we call 3D, it's not really 3D morphing, but here is a nice geometrical object, and you want to go from here to here, and you can really see that actually there is a progression in terms of the space where you zoom, really, and then slightly change also the point of view. So of course the nice thing is, and this is well known, if you have millions and millions of images of, for instance, a city, or if you have thousands of views of a given landmark, you can certainly reconstruct it quite precisely, just because you have enough images, and so you can interpolate between all these images. Again, going from one lightning of the moon to another. Here, I think, one thing which is pretty clear is that if our goal was really to have a nice and smooth transition, then we shouldn't use convolutional descriptors like we did, because these descriptors, they're trying to be invariant, especially to right, left flips, So you can really see here, for instance, that it's almost a mirror image of one another. If you really want if you wanted to be able to do like a movie, then you would need less invariant descriptors, maybe something like this or other. And then just for the fun of it, trying to go from, one object such as a flower to the golden gate you know, it's just fun to see, you know, like how you transition from, you know, like flowers, but seen from further away, more to grass structure, and then, you know, like to vertical structures, meshes, and then slowly but surely, you know, like go all the way to the Golden Gate view. Not sure there is much, you know, like application of this, but it was just fun to visualize. And similarly here, you know, going from a peacock to a cat, where, you know, really you can see first, you know, like how the peacock, you zoom out, and then it turns into jogger, football player, etc. A map, and then you slowly transition to babies and then cats. Again, you know, this was just for the fun of it. And dogs to cat. Yes. Again, fairly natural transition, which happens here between this and this. All sorts of things you can do from large quantities of data. Okay, so just to conclude, as I explained at the beginning, today there are two main strategies to encode your data into compact codes. One which is extremely fast but not very accurate because it constrains your data to lie in the binary space, and one which is, you know, extremely accurate for a given number of bits, but on the other hand, which is not as fast to compute because it does not leverage, you know, fast binary operators in assembler. So this polysemous code strategy, it really takes the best out of the both worlds by reinterpreting your PQ codes, your k-mean centroid indices, as binary vectors. And then by shuffling these indices, you can have an assignment such that the Hamming distance between these indices reflects the distance between the PQ codes. So I know that Hervé and Matthijs are working very hard to make this open source, but not by itself, as part of a much larger open source library called the Facebook AI Similarity Search Library, which will contain a lot of routines. So if it's a topic which is of interest to you, please stay tuned. And then what I showed you in the end was more like an application to building an image graph, and you know, what you could do with such a graph, some navigation, multimodal index clustering, etc. As for the future, as I mentioned, you know, what's not very satisfying today is that we really have like three steps to go from our three learning steps to go from our descriptors, our images, rather to our final code. The first one is this CNN descriptor extraction, for instance, with AlexNet. The second one is PQ quantization, which is unsupervised. And the third one, third phase of learning, is this reshuffling of the indices. And it would be good, you know, to have like a single learning procedure for these three steps rather than three separate steps. That's the whole point of deep learning. To be honest, the most obvious thing to do, which is like to join together the learning of the PQ code, so the k-means learning and the assignment of the indices. I think it's fairly easily doable, but we don't have much hope that it will make a big improvement in terms of accuracy. What we expect, like, you know, improvement is if we put the three steps together, but that's a little bit more involved, and I think will be a topic of future work. Thank you very much.
Thank you.
Have you applied this on RGB images, or you have tried other types of input data?
So the polysemous, I mean, all the PQ, Hamming embedding, you know, polysemous code, etc.